Okay, welcome all to the second and well, second or third, I don't know, the last part of the class where we introduce or reinforce or learn about derivatives and all this stuff. So it's nice to change topic once in a while. By the way, I realized last time that I went really fast. And I was like in my bubble and I was just computing my things and I didn't realize that until the end that I went much faster than I thought. So apologies, and I'll try to rein in myself. And if you think it's going too fast, just say, "Oh, please, sir, we can't understand." But yeah, it's so you have access to the lecture and you can like listen to me, but in 0.75 times speed. So that should do it. Okay, derivatives. So here's a motivation for the derivatives. Comparative statics. So have you heard of this term before, comparative statics, in your classes? Yes, no, maybe. No, don't remember. Maybe if I show you, you'll remember. So comparative statics is what we use once we have defined a model, solved the model, and then we want to just discuss what we just found. So we find the result and we ask ourselves, oh, does that make sense? How does this makes that other thing change? Yeah, so for example, I could just say what this is. This is like the big overarching theme, and this is a smaller theme there. So yeah, let me put this in. All right. So comparing different equilibrium states. When parameter value change. So what we want to look at is how will the variables that interest us, say we care about output or we care about production or prices. So we ask ourselves, so when this changes, how will these things change? So it's, of course, it's fundamental to economics. So example. So we have found in the previous example, we had Keynesian so we had found that I0 plus 2 0 plus 8 divided by 1 minus b. So the sort of questions that we may ask is, what happens to y star when I0 increases? So what we're saying there is what happens to output, the impact on investment on output. Will that increase or decrease investment? So then you could just give a qualitative answer. Which would be, what would your answer be? I know that to solve this, you need to solve a 3x3 matrix and find a determinant. No, I'm just kidding. You just look at the formula. No? Go up. Oh, I'm sorry. I'm insulting your intelligence. It's too easy a question. So, yes. So, answer, well, it increases. Or some other question. What happens to output when B increases? So here I don't know what B is. It was some parameter. And then again, here the qualitative answer would be, well, let's look at it. So B is has a minus sign on it, but it's at the denominator. So again, it's minus and then it's at the denominator. So if you decrease B, you will increase this fraction. So it increases. So that's qualitative answer that we may give. But then what we may want to do is go further than that. So what is quantitative answer? Such as the change, the rate of change, and the derivative. So this is where we're going. Note about this. Here we're not talking about transitions, so we're not saying, oh, if investment increases today, then in 2 months, output is going to start to increase. No, we have no notion of time. Here, what we're just looking at, this is the equilibrium output. And if we were in a different world where I0 was higher, then the equilibrium output would be higher. This is how we're saying. So this is a transition. RBC, for instance, or TSG, which you will not see right away, but eventually I'm guessing you're going to see that. But yeah, that's not here. We just care about this. Okay, so what is, first of all, the rate of change? And the derivative. Well, what's the change basically is, imagine that I0 was 1 and then it's 2. So what would y star be in case it's 1, in case it's 2? So you would say that you would sort of have a function of y star of I0, because I can define it as a function since I'm saying this is what describes the behavior of y star. And then I could evaluate y star for different values of I0. So the change would be if I change I0, what happens to y star. But we don't really care all that much about the change itself because it has units, it has contexts. What we really want to know is rate of change. So how something may increase in proportion to something else. Yeah, as a result of the change of something else. Yeah, so this is what we're going to see. So the rate of change, and the derivative is a specific rate of change that we're going to see. So you don't have to write this. It's just to see that. Yeah. Okay, so the difference quotient. This is what we use to describe the rate of change. So let y equals f of x single variable function. So for most of the time, yeah, for some classes, we're just going to have single variable functions, less complicated. What we learn here is okay, and then we introduce more variables. Then so when x changes from, so we're going to say it starts at some starting value x0, and it goes to another ending value or second value x0 plus delta x. Okay, so I could say it's x1 and define all my stuff in terms of x0 x1. Here I'm going to introduce this delta x, this change in x, which is quite nice actually. It makes I like the sort of notation it brings. Some of you may have seen the derivative in different ways, and yeah, that's all good. So a change, yeah, so when changes, x changes from x0 to x0 plus delta x, then y from what? From f of 0 to f of x0 plus delta x. So this is, imagine that I had I0 and then delta x is like delta I, so I would be looking at the change in y star. So the difference quotient, so this is the change. The difference quotient gives the change in y per unit change in x. So we just say that the difference quotient or the average rate of change of y when x changes from 2 0 plus delta x is this thing. So we just divide the both of them together. So we see it's going to be delta y. Yeah. I could even say that this would be include this, so the change in is delta y. Even better because I introduce more stuff. All right, so delta y over delta x. So I assume you have seen this before, which is what? The change in y divided by the change in x. So it's x0 plus delta x minus x0. And of course, this is why I introduced this delta x here, because the x0 disappears. So just have this. It doesn't disappear entirely. Why it doesn't disappear entirely? Because it's here and here. So f depends on x0. It does not just depend on delta x. So here the difference quotient or the derivative will be a function of where I start. Oh yeah, by the way, so who has seen derivatives before? Okay, so everyone or most people? Yeah, everyone. Okay, so it shouldn't be too hard. Well, this class, but in my experience, still this was the more difficult part of the course if I compare the. But maybe it's just because I accidentally gave a midterm exam that was too easy and the final was too hard. We'll see. The what? Yeah. No, well, it's they were not pleased. The class average was kind of too low for my taste. Yeah, so of course the problem is, yeah, and I would like to go faster and look at optimization and with many variables and stuff, but that's what you see in the next class, so I'm bound by my mandate. So just take it as at a leisurely pace. So yeah, it depends on x0, but also it depends on the change in x. Why? Because f might be nonlinear, and if I apply a small change or a big change, then it's going to change what this difference quotient is. So if I give an example, so let's have a very small, small x, y equals x squared, and I take x0 equals 1. And then the thing is, I cannot derive yet. I have to define what my delta x here is. So let's look at what happens if I take different length of delta x. If x equals 2, then what do I get? I get delta y over x equals 2. So yeah, x0 is 1. So 1 plus 2 squared minus 1 squared divided by 2, which gives me 4. If I take delta x equals 1, then I will get the following. 1 plus 1 squared minus 1 squared divided by 1. So you see that I'm slowly making the change in x as small as I can. Here, what do I get? I get 3. And of course, the goal is to go as small as possible. So let's look at delta x equals 0.001. And why do we want to go as small as possible? Well, because since f may be here, f is nonlinear. So what does it tell me to say that, yeah, from 0 to x equals 100, this was the change? Yeah, it might be interesting, but really what we want to know is how fast the function is changing at some point. And for this, I have to be as precise as possible. If I do this, I'm going to 0. 0.0, and I get much closer to 2. And just for the sake of it, since I have a computer and I type really fast, so let's add zeros. Maybe does it take it? Oh yeah, so now it says, okay, so it's too precise. Let's remove 1. Okay, so I have 1 more. So you get the point. The smaller the change, then I'm slowly but surely converging on one value, which is 2 in this case. Can I take delta x equals 0? Since what I want is a small change as small as possible. No, I cannot. Problem. Delta x equals 0, which is makes this condition. Yes. So we need as small as possible, but not 0. So there are different ways of doing this, but the most popular or one I'm sure most of you have seen is the limit. So that x tends to 0 of this fraction there. So solution, take the limit of of course, I'm going to be much more specific about what I mean by limits and all of these things. So that's what we're going to see today. Okay. So I have here made a small graph for you. Yeah, capture 12. show what's going on. Here, I've looked at two cases. So I start at 1, and I take delta x equals to 1, and then I get this change there. From 4 to 1, so y changes, it's 4 minus 1, 3. So delta y would be 3, and delta x would be 1. But here, if I take a very, very, very tiny delta x, then you see that the slope of this tangent curve there tends slowly towards what value? Well, 3 minus 1 is 2, and 2 minus 1 is 1. So it tends slowly towards this fraction of 2 divided by 1. And let me just also define other stuff. So definitions. I haven't said what this is. So second, straight line. Cutting line at 2 or more points. And tangent. So it's curiously not that easy to define it well, but I'm going to use Leibniz definition. Was a famous German mathematician. It's so I'm rephrasing his definition. I don't speak German. A second line, cutting a curve at 2 points. That are infinitely close. So it's also sometimes you see it's just touching. Yes, that sounds very unwieldy for the mathematical definition. But so why am I using this? Well, because the word tangent comes from the Latin, which means touch. So here's the tangent line within red that just touches this this function, whereas the second here intercepts it at 2 points. All right, so is that clear? So if I took an even larger delta x, then I would get a different value for delta y or delta x. So the goal is to take as small as possible. And here I see that if I take that, then the slope of this tangent line would be 2. All right. Derivative. So no questions. So everything is under control. Yeah, so it's the rate of change of y. When delta x is very small. So we say x is arbitrarily close to 0. So the derivative of y of f of x respect to x. At x0 is the limit when delta x tends to 0 of f of x f of x0 divided by delta x. Okay, so this is our definition. So it's the difference quotient, but with a very, very, very small change. This is the motivation of the derivative. And we could always use this definition and be good with it. Of course, that's not what we're going to do. Okay. Properties. Derivative. The derivative is a function a derived function from a primitive function and here our primitive function is simply f of x. So yeah, so it's still a function of x. But what's nice, it's no longer a function of delta x because I've chosen specifically one, a very, very small one, and then I don't have to care about which change did I use. Was it monthly? Was it yearly or was it a trimester? No, it was an instantaneous change. Yeah, so that's my second point. So it is also measure of the instant change, rate of change. And because the instantaneous change is 0, so it's what we care about is not the instantaneous change, it's the instantaneous rate of change. So the derivative is denoted in different ways. Some of you know them. Which notations we use? Or yes, so but do you know who came up with them? What's the name of the people? Here I have 3, so Newton, Leibniz, and Lagrange. All right. So here they are, given a function y equals f of x, the derivative have different notation. Okay, let's start with Newton. So he came up with his derivative in people say in 1666, but published it in 1687. So do you know, somebody knows the story of Newton that time? No? So, so he was about 23, so I don't know what your age are, but you are early 20s, I guess, so it's about your age. And there was an epidemic in London, so he had to flee to the countryside so he wouldn't catch the bubonic plague. And then he started he said, oh, I have time now, I'm just going to think about stuff. And he invented, optics, mechanics, the derivatives, law of universal gravitation, just in the span of like a year or something. So it's yeah. So most people say it's sort of the best scientific accomplishment that anybody has ever done in history. And he published it in 1687 is in his book. So his book is Mathematica. And people say it's the greatest book, the greatest scientific book ever written. Yeah, so very, very solid guy. And his notation is the following. So it's noted this way, y dot. And so this is for a single derivative, but since some of you know derivatives, let's just go a bit later. So you can have like y dot dot for second derivatives. But so we're not going to use that one. So it's mostly used for physics and derivatives with respect to time. Yeah, so he really just used this to describe his mechanics, and he didn't. I'm sure he knew that it would just for the mathematical purpose of it, it was very useful. But that's what he used it for. The most famous one is the Leibniz notation. By the way, I hope I wrote the last. Oh yeah, sometimes I had a T there. It doesn't have. So that's, and the funny thing is he came up with it in 1675 and published in 1684. So why is it funny? Well, because look at this. He came up with it later, but he published earlier. So in science, usually the first one who publishes is the person who came up with it. But yeah, there was a huge war between England and Germany, between Newton and Leibniz, to decide who had copied the work of the other person. And I think most of, in the history, we say that they came up with them mostly independently. They might have shared a bit of work, but yeah, the two of them have done much of original work. So, but yeah, for a very long time in England, they only use Newton notation, even though it's not a very useful notation, just because they said, no, Newton invented it. So that's what's useful about it. So we note it this way, dy dx. So it's, note that it's almost like delta y over delta x. So it's just dy dx, where just we say that d is a very, very small. Or you could also write just d over dx of anything. So for instance, you could write this for f of x. And you could write for a second derivative. So for instance, e squared y over second derivative. So it's used much more. It's what you're going to see in most cases. It's very, very useful. Yeah. And where is a very and finally, Lagrange notation. Y prime. So you see Y prime, like prime chicken. And it's like, but we mostly write this for f of f prime of x. But you could just say Y prime, but it's not as widely used. And for a second derivative, you just use Y prime prime of x or I mean, or you could also write f2 of x for second derivative. Or even what you can use is f minus 1 of x for call anti. So that's why it's a very neat notation, because it really looks like you can derive as many times as you like, and you can also anti-derive, so do the reverse operation. But don't worry, we're not going to go in this direction. We're just going to stay in derivative. Yeah. So that one is for single value function, or not, yeah, single variable function. Otherwise, if you have a function of many variables, then you can use Leibniz, or you can use something that's coming later. So for functions of many variables, example, y equals f of, let's use something of g of x and z. So the derivative of x of g with x is noted. So you can write it partial g of x partial x, or you can write it this way, gx of xg. So in that case, we have identified that we use x in the first as first argument, or we can also write it g1. So this is coming much later, but I just want to implant this in your mind so that you don't get surprised if we introduce many different notations. So this looks very much like Leibniz notation, but since we have many arguments, we say it's a partial derivative because we have to decide we derive with respect to what. And we also, so this is a very neat and fast way of identifying it. So we just write subscript X or subscript 1 to say that we derive with respect to the first argument. Yeah, that's for later. Example. So imagine I have y equals to f of x equals to, let's have a nice polynomial expression, plus 2x plus 11. So so I have the derivative at x equals 1 is the slope curve. And I'm not computing it right away because we're going to define lots more stuff. But this is what this would be. This would look like. Conditions of the differentiability. So questions about this? It looks like what we have already said. So what I want to take is the tangent line here. So and the tangent line is when it's a secant with where the distance between the 2 points is infinitely small. So it's just touching, and it is of course the slope. All right. So not all functions are differentiable. And mostly why, so when is a function differentiable? So the derivative of f of x exists if the limit of the difference quotient exists at x0 has tends to 0. And then we can see that a differentiable function is one that is differentiable at every point of its domain. Okay. So haven't introduced, so I've introduced a lot of concepts, but nothing really proven anything or haven't given you formulas yet. So that's where we're headed. But first of all, we're going to define limits. So questions about what we've sent so far? No? Yeah, so again, sorry for those who know all this stuff already, but so that's Actually, not sorry. It means that it's easier for you, so you can focus on your other classes. All right, notion of limit. Is the value of one variable as another variable approaches a specific value. So one point I said earlier is we use limit because everybody uses limit, but we don't really need to. So some mathematicians just describe delta x as a very, very small amount, and they don't have limits. They just say it's a very small amount, and they say what they can do with it, and they can very, very easily come up with derivatives without using this concept. But yeah, we're going to use limits because that's the standard program. So by approaches, we mean taking arbitrary values arbitrarily close to it without touching it exactly. So for a more formal concept, so you can look in Chan and Wainwright. And page 103. Okay, so we have different categories of limits. So some limits are easier than others. Take category 1. So we call this easy limits. Because what we can do is just directly substitute the value we're heading towards. So by direct substitution. So, but it's not incredibly useful, but yeah, so I'm just yeah. So for instance, the limit when x x goes to 3 of x squared plus 1 or x squared plus x over x plus 1. So you can always check whether you can just directly substitute. And if you can, then it's you're all good to go. So that would equal to 3q plus 3 divided by 3 plus 1. And that would be equal to 3. So that's an easy one because you don't have weird things happening, and you don't have problems at the exact value where x is, or where we take the limit. So 3 is not a problematic case. But of course, problems may arise later. So category 2. So not easy limits. So example, 0 divided by 0, or infinity divided by infinity. So which are by substitution. So example of that would be limit when 3x minus 6 divided by x squared minus 4. This would be when x goes to 3. Y. So if direct substitution, so I get so that's 9 minus 6, so that's 3. And here I have 9 minus 4. Oh, no, that's easy. Why did I say it's difficult? Yeah, no, there is no problem with that one. Okay, let's use another example. Thank God I tried to do it. Otherwise, I would just have puzzled everybody. And okay, so yeah, let's take a more difficult one. So what do I get here? I get 9 minus 6, 3, and then 9 minus 4. So let's have minus 6 here. Okay, so if I do that, I get minus 6 equals to oh no, that's fine too. No, I need 0. Also limit when this tends to 2. Maybe that's the problem, is I didn't change my so that's 6 minus 6. Okay. And here I have yeah, okay, that was it. I didn't change that. Okay. So then this gives me 3 times 2 divided by 2 squared minus 4. So I get 0 over 0. Which is uneven. Just move this. Okay. Last category. Two-sided limits. And here I have 2 cases. So case 1. So two-sided limits, what I'm saying is the function does different thing on both sides of the limit. So I have to care about estimating it when I tend toward the limit on one side or I tend toward the limit on the other side. So case 1 is that one. So you see that I have one function that's doing this, and then one function that's doing this. And if I take the limit at n, then I really have to make sure that what happens on one side and what happens on the other is the same. And then the second case would be that. So in that case, I don't, the limit is clearly different. So here, at least at n, the value of the function is the same, whether I tend towards the right side or the left side. In this case, it's different whether I go from one side or the other. And we're all going to see what happens when we try to. So what we have to do in this case is take the limit on the right and the limit on the left. So I will limit. On the right side. Let's take the right. And the left. So how we're going to know this is the following. So when we tend toward x0, but we're going to write a plus here, it means that we tend towards something that's slightly above x0. So it means that we tend towards this value there. So n, for instance, but with ever so small difference between n and n plus something. Of fx means or is greater than this. And then you can guess what's coming. So the left side limit so we see that we go from negative values to x0. So we need the limit when x tends towards x0, when x is smaller than x0. So we're arriving at x0 from that side. And then when we have two-sided limits, we see that the limit exists when the right side limit equals to the left side limit. Okay, so quiz. Does case 1 at n so just let you copy this. Okay, and here is again case one. So do we have a limit at n? Yes, you're confident, you're sure, you would bet your house on that. Yes, good call. Yes, because when I come from the left, the right, sorry, I head towards the value L. And when I come from the left, I head towards the value L as well. So since the right side limit and the left side limit are the same, then we see that the limit exists in this case. And then in the case two, does the limit exist? Well, no, because the right side limit arrives at L2 and the left side limit arrives at L1. Yes. So did I use N? And then does case two have a limit at N? No, because this is equal to L. So when I go from the right, equal to L2, which is greater than L1, which is the limit when I go from the left. Quiz. Does f of x 1 over x limit at x equals yes, no? No? Good call, good call. So no. So why? Because so this is equal to what? Well, yeah, I'm going to say it's for 0 plus. So no answer? Yes? Yes, infinity. And then the limit when goes to minus is equal to minus infinity. So do I have cut of this? Oh no, I don't have one. Here it is. So this the limit on the right side goes to infinity and the left side goes to minus infinity. So I don't have a limit. Let me try and make a nice print screen of this. So do I have a last one? Okay, another one. So f of x equals to uh, x when x is smaller than 1 and x squared when x is greater or equal to 1. That's f of x. And that x equals Are some of you confused by limits, by what we're doing there? So here, essentially, it's easy to estimate the limit at 1 because I can just substitute it. I don't have 0 over 0 or infinity, but I have to make sure that when I arrive from one side or the other, I get the same value. Right? I write it. Yeah, I wrote it. So yes or no? I'm going to lock the door and prevent everybody from leaving. Yes, okay, I have seen this. I'm convinced. So answer yes. So let's just compute it. So limit when x tends toward, we're going to write 1 plus equals to, so 1 plus, so it means that I tend toward 1 from larger values than 1. So I take this side there, so it's x squared. So it's, so I just take 1 squared equals 1, and the limit when 1 minus equals to, then I take this one there, which is 1. So yes, the limits are the same. Okay, so we stop here, and yeah, I'm going to send you some, well, put on Moodle some exercises for Friday, and there we are.